Okay, why don't we get started? So, I want to welcome everyone to the Fulton Schools of Engineering Dean's Distinguished Lecture. And we're going to do something a little bit different, perhaps, in the sense that my role is to actually introduce the person who will introduce the speaker. And the way to think about that is the Fulton Schools were very large, right? We have about 350 faculty. We're in the midst of another terrific hiring season. And the power of a large faculty and having gotten great people from great places, the people who've come over the past couple of years, the people who've been here for many years, is the power of connections. So we understand and we value partnerships, and oftentimes that's with an agency, a foundation, but it's also with colleagues. And many of our great faculty have come from great places themselves. And in particular, those connections then lead to an invitation for what I'm sure will be a very powerful lecture today. So, with that, what I'd like to do is introduce one of our faculty, Professor Barbara Smith. She's a faculty member in the School of Biological and Health Systems Engineering, and she was a member of Dr. Whitesides' lab. So that gives a personal touch and a personal flair that she can relate, and she'll introduce our speaker. So with that, let me bring on Professor Smith. Barbara.
Thanks so much. Thank you. Hi. All right. Hi. It is an absolute pleasure to be here today and an honor to introduce Professor Whitesides. I'm going to start off in the beginning, but I'm going to make it quick. Promise. So Professor Whitesides started his academic career at Harvard University and graduated in 1964 with a PhD from Caltech. And for the next 19 years was a professor at MIT and shifted over to Harvard. Since 1982, he's been a professor at Harvard. He has over 1,100 publications. Get ready for the numbers. He has mentored over 300 students, both graduate students and postdocs, and has invented over 50, is on over 50 different patents, started over 12 companies, and those companies have a net worth of more than $20 billion. He is extremely well known in the field. He is a member of the National Academy of Sciences, and in 1998, Professor Whitesides was awarded the National Merit of Science. So this is a man that we all know, and we've all read his work, and probably in soft lithography and microfluidics, point-of-care diagnostics, and today we're going to hear about it in soft robotics. And he's a man that started multiple fields, and probably if you have it in your lab today, it links back to Professor Whitesides' lab. He's a great thinker, and it's been a pleasure to know him for these last few years. And with that, I'm going to pass it over to George Whitesides. So join me in welcoming Professor Whitesides.
Thank you, Barbara. So Barbara left the lab how many years ago?
3.
3. I'm still exhausted, those of you who know it. So those of you who are here for a while, you have an exciting time ahead of you. I want to talk about an entry into a particular kind of robotics. And I know there are a lot of people who know a lot about robotics here, and some who maybe know a little bit less about robotics. So I'm going to try to make a mixture, just a little bit at the beginning of introduction to why robotics is interesting to me and why our particular type of robotics is interesting. And then a few results that are older, which sort of give an idea of how rapidly the field is moving, and then some stuff toward the end, which is all new, which concerns a key element of this area, which is when you have a robotic system, it's made of materials. The materials do things typically and historically under the control of computers and sensors and things of this kind. And one of the key areas here is, can you simply replace the computers and sensors by the materials? That is, can you make the robot run itself based on the properties of the materials? And why do you care? And the answer is simpler, cheaper, more robust, easier to work with. So I'm a believer philosophically in the notion of simplicity, and I'll come back to this as we go along. All right, so let me make a few remarks about soft robotics and actuators. I want to start with a question which is my generic question about everything in science and engineering, which is who cares? And then spend some time on why soft, and what is a soft robot and actuator, and what do you do with them? And one of the things you do with them is you hold your glasses on your neck. And I should say that a month ago, I had the second of my 2 cataract operations done. And I can't decide whether I see you more poorly with my glasses on or my glasses off, but actually I think I'll leave them on for a while and see what happens. But if I keep squinting in odd ways, it's not a neurological defect, it's not a stroke about to happen, knock wood. It's just that. And then what does material science have to offer? So let me just start by making a remark about robotics in general. When you hear people talking about robotics, particularly in the popular press now, there's a great deal of concern about the issue of robotics replacing people in work. Is this a good idea or a bad idea? What happens when all work goes to machines? Is this a good idea or a bad idea? And I want to just give you an example of a historical precedent in this, which is this. And in the mid-30s, there was a class of robots, actually 2 classes of robots introduced, which were washing machines and dishwashers, which released about 50% of the population of the United States, otherwise known as women, from doing dishwashing and washing machine-like stuff to do teaching and being CEOs and running telephone systems and doing whatever people do. But the point is not, do robots displace people from jobs, but do robots allow people to leave unpleasant jobs and to take on more pleasant jobs? And what's an example, to make things real? I look out at you, most of you, with gratitude. And you say, well, why? And the answer is that I'm getting older. The healthcare system has already spent down all the money that I put into it. So there's nothing to keep me going in my geriatric decline except you. So I expect you to be on the edge of your seat, working hard for me. And what does that have to do with this? And the answer is that one of the big problems in Western Europe and the United States and Japan is going to be elder care. And there's a lot of elder care, Alzheimer's, Parkinson's, just age, which have to do with, dealing with stuff that's actually not necessarily pleasant for everyone. So let's replace a lot of that to the benefit of everyone with what machines can do and let people do something else. The trick in this is what is the else that people are going to do. So we desperately need to find new work for people to do, and that's, again, up for you all to do. That's important. Okay. What would be an example of another job that you would like to replace? This is my idea of the end of human existence. This is an Amazon packing house. And it's a weird mixture of people who are doing a mind-numbingly boring job, which is picking stuff out of bins. Bins are brought to them by robots that are mobile robots. And it's really, really intensely boring. And what I want to do is to bring you up to date on a technology which actually doesn't solve this problem yet, but it's pointed, at least in part, toward the question of how do you take a bin of mixed stuff and then pick out the pieces that you want for different purposes. Which may seem like an interesting problem, but it's not. All right, so why soft robots? If you talk to people who make robots in general, and ask them what is their wish list, what do you want? The first thing that everyone says is collaboration. And what collaboration means in the trade jargon of robotics is you want robots that have the characteristic that they can work safely and cooperatively with human beings. And if any of you have ever looked at the pictures that you see of a Toyota assembly line, it is full of devices that are sort of half the size of the room, roughly, which can twirl an auto body as it's being constructed in 3 dimensions with perfect dexterity, with arms that, by the way, if they happen to swing this way and you're in the way, shear you off and never notice that you're there. They're absolutely non-cooperative. And so if you're talking about Alzheimer's patients, it has to be something that is sort of like a human hand. So that's what collaborativity means. How do you bring that to robotics? And that, it would seem plausibly to imply softness, and that's a part of the story. A second thing that people want is simplification. That is, they want simplified controls, they want systems to be adaptable. They don't want to have complex, elegant computers on their system. They want to have nothing there, ideally. They want the system to do it by themselves. The fewer parts there are, the fewer parts there are to go wrong. And that's an interesting part. And for those of you who spent a very interesting hour talking to people who love the complexity of computer-based control. I admire people who love the complexity of computer-based control. I want nothing to do with it if possible. So that's fine. So that brings up the idea of the computer as controller, as material as controller. And one of our ambitions in this is to make systems that have what we call reflexive materials. I mean, you sometimes hear the phrase intelligent materials, and I don't understand how a material can be intelligent. But I do understand how a material, given a given circumstance, can quickly and autonomously do something, get shorter, get harder, get faster, get whatever it can be. So how do you design that into materials? It leads to some very interesting problems. And then a bunch of other stuff like low cost and lightweight. And if you're doing, just to take an example, if you're doing surgery, you do not want to wash your robot when you're finished because it's expensive and you don't always get it to work. You'd like to throw it away. Well, that requires a certain class of materials. And so on. There are a lot of fairly obvious things there. The stimulus for all this stuff is, from our point of view, the scientific stimuli is first and foremost biomimetic. That is, we look at biology and we ask if we're going to make something that's soft and behaves like a human, what would you have to do to make it be soft and behave like a human? Well, we're a long way from that, but that's the basic underlying idea. We don't start with the idea of how you build elaborate controls. We start with the question of how a pair of human hands functions, and then ask if you can do something with that. Simplicity and what we call stackability. Stackability is a word that we've made up, which actually I think is an interesting word. If you think about a computer system, it starts with transistors. A transistor individually is actually a pretty complicated device. I mean, it does very subtle things. But they are now manufactured in such a fashion that you can get billions of them at a time with zero failures. So you don't have to worry about transistors. It's now a done deal. So you now take transistors and using the miracles of photolithography, you can make them into integrated circuits that have a billion of them. And that's probably one of the great constructions of the human mind. Works perfectly, so you can forget about them. You make microchips and you just buy the microchip. And you take the microchips and you put those together and you make computers or whatever you have. And they work so well you forget about them. At each level you take a technology which can be very complicated, but you make it work so perfectly that the next level of user never has to think about how it works. And so the question with robotics to me is that if it is going to be something that is everywhere, the individual pieces are going to have to work layer on layer perfectly. And what that means is as few controllers, as few computers, as few everything of that sort as you can possibly have. Simplicity is really helpful in the world. What else can I say? It's not a question of just saying, it's a question of, two other things. Being able to read, because I can't both see you and read at the same time. One is the question of tethering. There are arguments about whether you want a robot that's entirely self-powered, because we're self-powered, except we've got to eat every once in a while. So with computers and with my computer and with other systems, you build batteries in. Okay, I mean, that works. But many robotic systems are actually run with plugs into the wall or inlets to power systems of other sorts, mostly pneumatic. So I'm not at this point very concerned with whether it's tethered or non-tethered. That's just a question of where you put the power source. The other issue is a word that's a little bit more complicated in its meaning, which is autonomous. And autonomy doesn't have a really clear meaning, but in this context, what it means is that the system, faced with the necessity to do something, does it on its own. It's not controlled in doing it, it just does it. So it's autonomous, it makes its own choice in a sense when faced with a task. And I'll show you a lot of systems that do that. So all interesting problems. Now I want to show you one of my favorite movies, which, if assuming it runs, which is a non-cooperative robot. And this is a fairly old Boston Dynamics system. But the first thing you would say is that you don't want to hire that as a babysitter. But this is the picture that's really worthwhile looking at. Watch the way this moves. And it shifts its center of gravity, it rebalances, it does everything that it does in a way that I think that if you blur your eyes, you can't tell it's not alive. I mean, it really looks like a horse or a pig or something like that doing, pigs don't throw concrete blocks, but you get the idea. And it's breathtakingly clever. But the thing you have to understand is that it has no brain. There is only a collection of gyros and accelerometers in that, and there's no central processor and no central intelligence. So what? You say, well, the trick is take something like that which works so well that physically you can't really tell whether it's alive or not, and combine it with artificial intelligence, and then wait 10 to 20 years. I don't really know what we're going to see, but I don't think we're going to be able to tell those constructions from things that are alive. So we're doing something that's really interesting, which is we're doing what's called in the trade, we're evolving a peer competitor. That is a system, in this case not alive, or at least not at the moment, which can do the same kinds of things that we can do, in some cases better. Though maybe it'll look different and maybe it'll have other inner characteristics, but as soon as we in technology start doing that, then it's an issue. Now let me just give you a little bit of a guide to some of the things that come in a bit. This is what we would all say was a biomimetic system. Come on, go backwards. Oh, no. Here we go. Here. Biomimetic system, that is a bicep. It's not, relative to most of you who are young, it's not an impressive bicep, but it's a bicep. The question is, can you mimic that? And I want to show you a method of mimicking it. But it's not trivial. It's actually pretty interesting, but it falls in this area of stackability. It's based on nonlinearities of material in a quite subtle way, but it's absolutely reproducible. Works perfectly. And that's what it's going to look like. So we're going to make something in which the operative device is that sort of purple thing, which I'll show you how it works in a bit. Now, one more last kind of background thing. This is for those of you who are thinking about being entrepreneurs. This is actually important. We're interested in simplicity, to design, to make, all the rest of those kinds of things. But you also want to have a technology that has the characteristic that at the end of the day somebody cares about it. It's actually not produced just a paper, but it's produced something that has an impact on society. And how do you do that? And I'm not in general in the business of shilling for books, but let me shill for a book because it's a very good one to read. It's this thing that you see here by a guy named John Garnier. And it's a history of Bell Labs. And I hate histories of Bell Labs because they're typically physicists advertising for physics in a way that says, brilliant physicists operating unconstrained by financial constraints, invented solid-state physics, invented the transistor, invented the internet, changed the way your children's brains are wired, and all the rest of that. And what the guy who was the head of the laboratory there, Bill Baker, said is they were brilliant. There's no question that Shannon and Bardeen and the rest of these guys were fantastic. However, they were hired to and signed up to make a more profitable telephone system. They did all of that work because people in New York wanted to place bets on hog futures in San Francisco, and they couldn't do that. So the issue there is that they were doing it not for the greater glory of science, but to solve a problem. And the problem was, how do you make a system of switches that worked perfectly for transcontinental communication? Now, what's the lesson for people who are interested in starting technology? Because there's no question that Bell was fantastically profitable at that. And Mr. Baker talks at length about innovation. And all talks about innovation, or much of anything else, international conflict, love and hate, have four components. And the reason for that is I have 4 fingers that I can hold up easily, and a 5th is superfluous. So what are the 4 components? Well, the first one, in his view, is you need science. And I think he felt you could get science almost anywhere. It wasn't very expensive and very hard to get, so you just get some science. And then you do a step which he calls invention, and what I think he meant by invention was largely making a functioning prototype of what you think you want to do. So you've got to do the science, and the science generates this prototype. And then you do something that's hard, and that's what he called development, and that's engineering, setting up a manufacturing line, doing regulatory clearance, thinking about all the stuff that you have to make when you have something that looks like a product. So you get finished with all that. It's expensive, it takes time, and so now you've started with science and you have a product. And his sharply focused question is, what is the value, now that you've gone through all this, you've got your product, what is the value of that? And he says 0. Whereas the only thing that counts, in his view, is the market. And what a market is a social construct that has the interesting characteristic that you perform that most intimate of human interactions, which is somebody writes a check for something because you have it and they want it. And that is, it's actually, the market is sometimes misunderstood. Because people think about market and money as something that you get personally. Actually, in almost all entrepreneurial stuff, the market and the money that you get personally is such a small amount of money it isn't even worth worrying about. What mostly happens in a market is that somebody says, I like what you've got, I'll pay you for it. Then you take that money and you make it even better. And that means they'll buy more of them and they'll pay you for it more. And there's a cycle in which the stuff gets better and better and better. And if that doesn't happen, you don't have anything. So one of the ways in which you make a market is that you find something that's an entry-level product that people want and they'll pay you for. I'm going to tell you a little bit about that. So let me just summarize some early work to get to a point, which is what you see on the left-hand side here is a picture of what we call a starfish gripper. And I'll show you how this works in a bit. It's an inflatable business, basically some blow-up balloons. Here's a raw egg. You lower this gripper on the raw egg and you inflate the balloons and the arms of the balloon wrap around the egg. And the nice thing about that is that you can't apply more pressure to the egg than you apply pressure to the balloons. Basically, that's all you can do. So you can't break the egg. That actually turns out to be a hard problem in robotics because you have to have sensors on the fingers to make sure you're not applying too much local pressure. You have to have controllers. You have to do a lot of other stuff. It can be done, but it's not trivial. It's trivial to do this. It's trivial. So the part that's interesting is this. We invented this stuff and published a paper on it in 2011 or something like that, much to the resistance of the journal, or the editors, the reviewers. And in 2016, the company that came out of all this is an initial product. And I'll show you what these things look like in a moment. But for those of you who do this, to go from a first publication to a commercial product solving a problem in 6 or 7 years is really amazingly short for a manufactured thing. And that worked only because we've stripped out all the computers, all the controllers, everything except something that's about as simple as you can make it in terms of material science. Works, it's okay. So here's how you make these things. You simply, this is probably, let's start over here. You take this, think of this as a balloon, here's the cross section. And if you blow up the balloon here, what happens is it swells and nothing very interesting happens. This is thicker and it doesn't go anywhere, and this gets bulgy here and you end up with a shape like that. On the other hand, if you put a little reinforcement in here, that can't stretch because paper can bend, but it can't stretch. But this now, the thicker part, can swell. And so what happens is this stays constant, this bulges, and you now have made a gripper because you've taken something from there and it's done that. And this is a very simple idea, but it actually works pretty well. And the details of how you make this are relatively trivial. The one thing that's made a big difference is that this is all molded. We use 3D printers for molding, and the 3D printers are perfect for making the masters for these things, so that we can have an idea what a structure looks like at 8 o'clock in the morning and have a prototype working at noon. And a key thing in all cycles of invention is to make failures occur as rapidly as you possibly can. So a key thing is not to succeed fast, but to fail fast. If you do that, you're in good shape. So here is the device actually working. It drops down, you blow air into it, it goes down very gently, wraps its way around, and then picks up the egg. And it can't break it just can't do that. So it's a reflexive system. If there's too much pressure at some point, that pressure is adjusted by simply transferring pressure to someone else, someplace else. Now there's a very interesting thing here, which now starts to be something for the techies. And the second part of the talk, I'm going to show you a lot about this. If you look at what's going on here as this particular thing blows up, you'll notice something really quite interesting, and that is that these fingers, which have uniform pressure from here to here, start by curling at the end. So it curls at the end. Why does it do that? And that has to do with a situation that's crudely understandable by looking at this picture. Here's one of these curled tentacles. And the first bladder that's down here has nothing on one side and something on the other side, so it's a little easier to blow up than the second bladder. But there's a progression, which means that this will blow up first, and then that will propagate down this. And it's not completely obvious, but it's the way it works. This is a nonlinearity of materials, and it's very useful. And I'm going to spend a fair amount of time talking about other ways of doing that. Now, how about reality? Let me show you a real system. This is where these things are in a glamorous market, which is handling celery and dough balls and things of that sort. This is in real time. And the only thing that we do is to make the effector on the end of this. When I say we mean the company. But the characteristic of that system is that the grippers are compliant and they adjust themselves to the shape of the celery. You don't have to know what the exact shape of the celery is. All you have to do is get approximately there, and it works. So, I mean, it works most of the time, but that's okay. And tomatoes are an example of something which is soft and actually very easily damaged. This does about the same thing that you do if you were to do it here, only it does it faster and it doesn't get terribly bored while it's going on. And in reality, you don't always get all of them, but there's another one of them just with downstation. And then if you want to pick up cooked sausage links or other things of this sort, well, you sort of get the idea. But the point of interest here is it does slippery things. It does, the slipperiest thing it turns out you can find is skinned chicken parts. They're very slippery. I suspect fish are the same way. And vegetables and dough balls and all kinds of things of that sort. And so the market for this turns out to be food processing. Now, is that a big, exciting market? Yeah, it actually is enormous, because the food industry wants to take people out of food processing lines. And then the thing beyond that is what you do in CVS and things like that while you're unpacking crates. So you're doing sweaters and bottles and all that kind of stuff. These are potentially enormous businesses. And it's not what I'm interested in and not what I do, but it's nonetheless very interesting. And it provides a market. Now, here's what we're going to do to talk about the technical stuff. I want to talk about buckling elastomeric beams. And you may say, is that really interesting? And the answer is yes, it's really interesting. Negative pressure, which means vacuum. I showed you how to blow things up. What happens if you suck them out? And then nonlinearities and materials response. These are sort of our three things for the moment. And let me start with beams. You all know that if you take a concrete post and you have a post and you start pushing on the post, nothing happens for a while, and you push hard enough, build enough of a load, eventually the post crumples. And once it's crumpled, once it's buckled and broken, it's not fixable. This is irreversible. You see the same kind of thing here with damage to an automobile. I mean, all this was steel beams to protect the inhabitants. But once it's damaged, it's damaged. But this is a rubber beam, and when you push on it, it buckles, but the buckling is reversible. And this very simple idea that you go from something that's buckling with a rigid material where the entire community of material scientists thinks of it as a mechanism of failure, you go to a soft material, it becomes reversible, and it becomes a mechanism of actuation. So often good ideas are just sort of looking at something and say, well, everybody assumes it's that, so it must be that. It's not more complicated than that. So here is the sort of scientific basis of this. Let me show you what's going on there. That pink thing that you see is a composite of air and a silicone polymer. So it's holes in a piece of silicone polymer. And our colleague and friend Katja Bertoldi studies this stuff. And you notice as you squeeze it, what happens is it does a pretty complicated thing. These holes break up into two lattices of things this way, and there's a phase transition. And so if you look at the stress and versus the strain, in this region where it's just closing, it does this, and then it closes over and does that. So actually pretty interesting behavior for a structural polymer. But it turns out that this is complicated to replicate because you're trying to hold it with your hands and squeeze it uniformly on all sides. So Dian Yang, who is working on this, had a very good idea, which was you take one of these systems of things like this, you put a thin elastomeric film on the top and bottom, and then you suck on it. And what happens when you do that is that atmospheric pressure is uniform everywhere on the outside. So automatically you apply completely uniform pressure on every exposed outside piece. So it converts the problem of making this kind of motion reproducible into something that's trivial. And when you do it, you find something that's interesting. Now what I want you to do is to look at this to the extent you can see it here and think of these pieces here as beams. You know, they're holding things apart. And as you suck it out, what's going to happen? The beams will collapse. And when they do, what they will do is rotate. So this will be a way of converting a simple actuation, which is the, here we go. Yeah, which is just applying vacuum to this system. What it does is to convert that into something where you have rotary motion. So it's a very complex conversion. A very complex conversion of motions. Let's see if I can get that to do it. I forget what. No, but this will serve as well. This serves to illustrate the interesting nonlinearities with that vital task of picking up a toy elephant. And what happens here is we have one source of actuation, which is negative pressure here. This is connected to vacuum. This thing lowers onto the elephant. Please lower onto the elephant, if you would be so good. And when it does that, what it does is the same motion takes the two arms and moves them in opposite directions. So it's actually a lot of different stuff going on with a very simple input. And that's what we like to see. Okay. Now, to get back to my arm, what we did here was to build a structure consisting of a series of beams that are rigid and then beams that are sort of more bendable. When you suck on this, these spaces decrease in size. When that happens, the whole thing crumples. And when it crumples, it gets shorter. So this is what goes on. And let me show you with that piece, which is the kind of thing that, here we go. So you suck on it, goes up. It's picking up a 5 kilogram weight, so it's actually a pretty hefty piece. So what that gives you is a linear actuator that enables us to do this. Now you say, is this the crown of creation? Well, I don't know. I mean, if you look at it, it turns out that that's probably the closest thing anyone has come to mimicking the function of muscle. It's about the same efficiency, the same speed, the same kind of thing. And it's very simple to make once you know how to make it. It's perfectly reproducible. These systems will go through 20 million cycles with no evidence of degradation in performance at all, which you can't get with most flexible systems requiring cleaning and lubrication. So they're very, very reproducible systems. And you know, the motions, this is not a very interesting motion from many points of view, but it actually is pretty subtle to be able to do that. So that's one example of all this, the efficiency I'll pass by. Now, let me go to, this is all useful. Let me go now to one of our projects which we do for, in principle, amusement. We call it Life That Never Was. And what does that mean? It means that if you look at the creatures that are around, you find that they walk, they hop, they swim, they do whatever they do, and that's all fine. But you can imagine that there are lots of other ways they might get around. I mean, there are many kinds of motions. Why aren't any of those used? And there's been no good way of answering that kind of question because you couldn't make any of them. And what we are now able to do is to make all sorts of simple systems that might have occurred in some organism at some point and see whether it does anything interesting. And what I'm going to do is to show you one test case in this which suggests that there's more than I would have thought. It's actually pretty interesting. So this is work that's based on a collaboration we have with one of my colleagues whose name, like many rock singers, he has one name. His name is Mahadevan. And you say anywhere in the world of condensed matter physics, you say the name Mahadevan, and people say, oh. It's like, you know, all the great rock singers. So Maha, and who's Maha, we use Mahadevan because his second real Indian name is about that long, and it has 27 syllables, and it's not pronounceable. Maha's a very interesting guy, and he got interested in the following question. Suppose I take a coffee cup, and I put a sheet of plastic on the top of it, and I put my finger here and I push. What happens? I try to shove this sheet down into the coffee cup. The answer is that if you do it the right way, it'll fold in, but it has to crumple up to do that. And that crumpling up is a buckling. That's another kind of buckling. So we got interested in this kind of buckling because one can easily imagine an organism that just made a sheet of stiff something, collagen or whatever it might be, and put some mechanism on for pushing on the middle. So what we're going to do is to make that kind of system. This comes with dramatic music. I didn't realize there was music here. But what we're doing here is simply pulling on the background. We're sucking on a bladder here. And when we do that, this thing undergoes this complex motion. Now, those of you who are robotics people, ask if you had a series of cables and stepping motors and things like that, and you tried to replicate the complexity of that motion, it would be very difficult to do. To just look at crumpling, it is actually very good. And you say, all right, so it crumples, so what? All right, fair question. Technology, probably not so important. These will go through many cycles. Here's the thing that's important. And that is that when you take this crumpling sheet and you simply put some, actually, there. It actually gallops pretty good there. And the question is, if it's so easy, if all you need is one sheet, some primitive legs, and one device for applying pressure, why hasn't somebody used it? This is actually one of the better walkers we have. So I don't know. I mean, I think it looks pretty good to me. And here's the bottom of this. And you notice it even does a sort of hop. So we will now go off and see what happens when we make walkers this way. I'm very enthusiastic about this. And you can make things that look like that are unusual shapes, and you can make it out of things of this kind. You know, it isn't restricted. Now, here's a sort of an interesting thing as well. And that is, if you take one of these sheets and you bend it, then when it does this crumpling, it will always crumple there. If you bend it in two places, it will crumple in both. If you bend it in three places, it'll crumple in all three. So what you can do is to program this non-numerically by just bending it, because it remembers the stresses that you put into it. We haven't yet determined whether you can unprogram it and reprogram it in some other way. But this is, I think, a really interesting idea of how you do programming in a purely analog way without any of the numeric stuff that goes into what we normally call programming. And it, again, works quite smoothly. And let's see if I've got a movie here. Yeah, here's a movie. That's a system that's been programmed to give four buckles. And it'll happily go on and give that kind of shape. If you ask me, what do I want to do with that shape? Right now, I have no clue. But that's okay. And here was the picture. This is a little bit out of order. Before I showed you the thing with legs, I should really have showed you this. And imagine that you're an organism and you're on a sandy beach. And what you really would like to do is when there's a shadow that passes over you in the water, which could be a predator, you just want to go somewhere else. And what's the simplest way that you can imagine to go somewhere else? And the answer is probably this is as good a way as anything. This moves along pretty well. It doesn't have much except one sort of pushing edge and one sliding edge that could be fixed up a little bit. And one actuation, which is easily done by even very primitive organisms. And I would think that if I were an organism, I would be very happy being able to move that far rather than just sitting there and waiting and saying, come eat me. So, you know, the extension is that you go on from there and you put on legs, but that was out of place. All right, here we go. So there, you've seen that. Now, what next? What's next in this area? I've given you a sort of an idea of where stage 0 is, rapid commercialization. Stage 1, which is the discovery that buckling is interesting. Stage 2 is the idea that there may be things that you can do with buckling, and there are many different kinds of buckling that people have never thought of because they never thought of buckling as being something that anyone would want to do. You normally want to prevent it from being done. So where are we now? We're going to exploit these kinds of things, but the major thing to point out is that if you think about what I've shown you, it's all elastomers of this sort. They're like rubber bands. PDMS is commonly used in breast replacement and tissue replacement. It's that polymer, so if you have a feeling for those objects, you sort of know what the consistency is. But here's something which has the characteristic that it's another elastomer, and it's very soft now relative to these things. And then I happen to be particularly interested in this, which is the basis of what we're calling hypothetically hard soft robots. If you're looking for something that is really, really tough, you don't use steel, you use rubber, particle reinforced rubber. And if you look, the things that form the basis for truck tires for heavy duty mining and things like that are all particle reinforced rubbers. And so that's one of the things we want to work on. A very interesting number in this is you say we apply pressure, we apply vacuum. How much? How much is required? 7 psi. How much is 7 psi? 7 psi is half an atmosphere. So it's half of what we live in. It's getting to be what you see toward the top of a very high mountain. And you say, well, that's not very much, is it? And there's an interesting number, which is the difference in pressure between a 747 in flight. The difference in pressure between the top of the wing and the bottom of the wing is about 7 psi. It's the same amount that we use. And we say that can't be the case because you're lifting up this entire airplane. But remember, pressure is force times area, pressure times area. And if you simply do an envelope, back of the envelope calculation and ask how many square inches there are on the wedded wings of a 747 and multiply it by 7, it turns out to be in the order of 1 million pounds, which is about what a 747 wings. However, it's really easy to go to 100 psi. And if you do it a different kind of way, you can go to 1,000 psi. And you know, these things are a couple of 100 psi. And we're all quite comfortable using bicycle tires, racing bicycle tires that are 100 psi. That's, when it goes bang, it's a big bang, but nobody gets hurt. So 100 psi at the scale that we're using, you know, something like this is 100 pounds of force. And something like this gets to be a ton. And so I think it's going to be actually pretty straightforward to build systems of this sort, which will do one of our group's ambitions, which is to tear an automobile in half. I hope we do it soon because I don't have that long to wait, but I really would like to see that happen because I can use that to confound some of our enemies. So, but if you look at this, there's an entire program here going from very, sort of ordinary elastomers to very soft to very tough and very hard, which will make classes of these soft robots of almost every sort that you can think about. Really interesting. Now, just very briefly for those of you who are students, what do you care about? Market opportunities, e-commerce, picking things, agriculture, of all sorts, food of all sorts, consumer products, and then for heavy industries, if we start doing some of these other things, lifting, working with toxic chemicals, working in radioactive environments, places where people don't want to work. These will work well there. And actually, in many of those, you can't send computer systems in. If you tried to send computer system into Fukushima, you fried the electronics essentially instantly. Here you don't care because these are really easy things and they crawl over stuff. Biomedicine is interesting in hazardous jobs of a variety of sorts. So a very wide range of things that you can do with soft systems. Some of the more intellectual things, I think this idea of replacing controls by the properties of materials is actually a good idea. Now, I don't know how far it's going to extend, but I have the idea that taking computers out of stuff rather than making computers more complicated is actually a good thing to do, simply because it increases robustness and decreases price. And also computer systems, they typically don't work very well underwater and in very hot environments and things of that sort. Nonlinearities in materials, a problem, and it's a very interesting one. If you talk to the conventional hard robotics guys about this, they say, well, this is all fine, but you're using compressed air. And they say that with condescension dripping from their lips. You say, well, what should I use? You say, you should use electricity. Have you heard of it? And all this conversation is not kindly intended. You say, well, why do you want to use electricity? And they say, you didn't hear me. I said electricity. I said, no, I hear you. You said electricity. Why electricity? You said, you're not listening. I said electricity. So this gets to be not a very useful conversation. But I don't know why one necessarily wants to use electricity. I actually like pneumatics because they're not much more complicated. They're safe. They don't short when you put them underwater. There are a lot of things you can do with them, so I like that. And then a few other things that you can read. And finally, there are a whole bunch of scientific stuff which you can read while I'm talking. But one of the nice things about this comes at the bottom here. These are so easy to make. These systems are so easy to make that you can actually think about doing stuff like this. And we have interns come every summer, and your interns come expecting to wash dishes. And instead, we have them make their own soft robot because it's so easy to do. They love it. They just think this is a great thing to do. And I think when you make science both interesting, simultaneously interesting, and really easy for people to work with, it's a good thing to do for the S&T enterprise. And so that's one of the nice things about this. Now, I've already shown you my prejudices there. Let me finish with this. This is a list of people who've been involved in this project over the course of now probably a decade. And you won't know the names, but what I would like you to look at is not even what they did, but where they come from. And you'll find some Americans there, but a lot of Canadians and Iranians and all kinds of people, German, Turkey, Canada, Iran, Canada, Scotland, whatever. And the argument is an argument that's very familiar here, but I think we really, as a community, need to beat on this. And that is, these are smart people who are curious, who are doing the work that's made this possible because they're smart people and they're curious. There aren't an infinite number of them in the world, and the United States needs to compete for them. So anything that can be done to block this issue of making it hard for foreign immigrants, particularly people who are particularly talented, to get into the United States, we need to really resist. We can put up with a lot of other stuff, but basically science progresses on the basis of people. And this project, to me, we could never have done it without people who came with totally different backgrounds and totally different cultures. So they did the work. There are some people who reluctantly paid, and I'm reluctantly grateful. It works out well. And I thank them, and I very much thank you, and I love talking to engineers. It gives me a feeling that reality is not entirely lost in the world. So thank you for the invitation to be here.
So thanks very much for a really terrific seminar. We do have some time for questions, and I think one idea is to get the microphone into people's hands if they have questions. Who wants to go first?
Yeah, on your par buckling sheets, or your buckling sheets, how do you get a directional motion? Why don't they just stand in place or wander around randomly?
Because the buckling, of course, makes the circular sheet unsymmetrical. And so it will always buckle in the same place. And when it buckles in the same place, what happens with these things is the tailing edge digs in so it can't go backwards, and the front end, because it has less in contact, can go forward. So that's, the sort of basic notion. These are also pretty good swimmers. You can make jellyfish out of them and things of that kind. But they're intrinsically asymmetric as soon as they buckle.
Yeah, fascinating talk. And so you have so many ideas. So where are the sources of your infinite number of ideas and also boundless energy? And we have a lot of students here. And what made you to do your PhD? And two questions. Okay, so you can encourage our students, right?
There will be a late dinner at midnight as soon as I finish this, so it'll be perfectly okay. No, the origin of this project is actually a little bit interesting. I've worked for years with various groups in the DoD, and one of the groups I've worked with is something called DARPA, which many of you know, the Defense Advanced Projects Research Agency. And they've been interested, of course, the military's been interested in robots of all sorts for a long time. But there are problems that come up which current systems won't actually handle. And an example of one is, how do you get a robot that can walk through surf onto a beach? Crabs do it just fine, but robots don't do it at all well. So the question was, if you look at existing life forms, and you say it doesn't have to look like me, it doesn't have to be bipedal, it doesn't have to have 2 arms and 2 legs, but you're free to look at anything that's alive and ask what's there. Then, since I like simplicity, my view is you look at starfish, you look at worms, you look at snails, and in particular you look at octopoids, because there's nothing more sophisticated than an octopus or cuttlefish. And so we set out, after some years of discussion, we got a DARPA project whose idea was to, I won't give it its informal name, but anyway, the idea was you want to start with an object that looked like a Coke can, would spontaneously unfold itself into a flat sheet, spontaneously walk across the floor, find a door jamb, crawl under the door jamb, and then reconstitute itself onto a Coke can on the other side. And you can see why DARPA might be interested in that. I was not particularly interested in that, but that's okay. But we set out, as in many good projects, set out to do it. And we didn't get the whole thing, of course, to work, but every component of it worked. That is, we were able to individually get all the components to work. And so once we sort of had this idea, and a lot of the ideas are just trivial, but for example, are you going to use chemical actuation? Are you going to use external pressure? Are you going to use electricity? Are you going to use magnetism? How are you going to do it? Once you sort of settle on some of these basic ideas, which can take a while, then a lot of the rest of it actually almost doesn't require any thought. And for those of you who are students, the thing to remember is that if you're the first in some area, then everyone who works in the area afterwards works for you. If you're the second in the area, you always work for whoever was first. So there's a lot to be said for being first. And does that answer your question? I mean, intrinsically, I'm immensely lazy. So, the idea is to do things that are first so you don't have to worry about all the people who are second and third and fourth and fifth.
So trying to replace any human activity by a robot. And robot doesn't have a brain, doesn't have a heart. So in cases where, human beings and people, don't like to do certain things, definitely robot is helping.
Yeah.
Risky job and all. But in some cases, a service, like you go to a restaurant, all the robots are, serving you with food and all, so there is no human touch.
Yep.
So what is your thought on that when you
Well,
have no human
my
touch?
first thought is I know many humans who have neither a heart nor a brain. So I don't see this necessarily as a disadvantage. But it turns out that increasingly there are cultures in which people are actually more comfortable operating with machines than operating with humans. I mean, apparently it's one of the big motivations. Well, a clear example is emoji. You know where emoji came from? Emoji was invented in Japan because the Japanese have a difficulty in expressing emotion in text. And emoji provided a way of expressing a kind of emotion in text without having to write something out. And of course, it's spread worldwide because it does all kinds of interesting things. But different cultures have different feelings about this. And so I would, in fact, far prefer to talk with a robocaller than I would with a human, because I feel no sense of guilt in saying clunk with a robocaller. And with a human, there's always, the fact that here's this poor person who's being paid in calls per hour, and should I listen politely for 5 minutes so they get credit for the call, or should I not? So, I mean, I think the point is legitimate, but the issue of whether you're 10 years down the road and the simulator of a person who's invariably friendly and invariably courteous and recognizes immediately what kind of joke that you want, and can be tipped on your Uber account, so you don't have to worry about any of this other stuff. I don't know what we're going to come out liking best, but I think it's actually it's a question that could make you a little uneasy. I plan to be dead by then, so it doesn't make me uneasy at all.
This can be a little bit of a philosophy question. So in terms of the general biomimetics idea, do you believe that in someday everything of organisms or lives can be decoded by physics?
I don't, well, how do I put this? Some of my best friends are physicists, but physics doesn't solve all problems. So I don't know the answer to that. I think the issue that's interesting here is not actually the human part, the robot part, the machine part, the AI part. It's when you put them together. What happens when you actually do a fusion of living and non-living and artificial intelligence and all the rest of that? What does that look like? And I don't think we can look at that with any more clarity of foresight than you would have had if you could. Some of you will remember when transistors came in little cans with 3 legs and you soldered the 3 legs into the device. I had absolutely no idea what would come of transistors. And the trick in this, as with transistors, is going to be to make all of this stuff, these functions, so reliable, so simple, so inexpensive, that you can use any number of them that you want in any way that you can reconfigure them and see what comes out of it. And we can't predict that. So what you want in a good area is something where there's a big there in principle. That I'm positive of. I don't know what form it's going to take. So that's up to you to figure out. You.
In many of the other fields you talked about, there are ways of modeling those systems, like in transistors we use like HDL and Verilog to model that. For these new soft systems, is there any modeling that exists currently?
The answer is very primitive. Katya does some of this stuff with regular arrays. But I think that one of the interesting characteristics of these very nonlinear systems is that it may be that we don't have good analytical models, but we do it by AI. That is, you simply make the thing, let it wander over all of its phase space, give it every possible motion, let the system remember all of that, and then you never know what it's doing, maybe, but it does it. Now, downstream, that sounds bad because you're trying to stack a system of things that are basically being operated on principles that you don't understand, and you have to think about how one layer interacts with another. I don't know what to do about that. That might be a problem or not. So right now, nonlinear mechanics and elastomers is a pretty primitive area because nobody's been interested enough to do it. That doesn't necessarily mean it can't be done.
I have listened to you many times, and I always get excited by the new vision you are painting, and it is always thoroughly enjoyable. I had a question which you might have answered partly with your response in the last one. As we move from simple, so to speak, functions like those you described into more complicated ones, where certain complicated logic may be involved, what sort of scientific technical directions in the areas of materials should we somehow start pursuing, asking questions in them in order to provide, quote unquote, logic, more complicated logic to simple mechanical motions?
I think there are a couple of answers to that very good question. One of them is that I think we'll be able to build systems which are logical. We have 3 or 4 now in which we can undergo all of the, and or whatever kinds of simple logical operations, whether those are not going to be useful in competition with electronic systems for doing logic, but they may be useful for doing simple information processing of some kind in building the machines. But I think more interesting is I've emphasized the idea that I would like to take sensors out of these, but that's not going to work. You're going to have sensors of some kind. So building materials that have the characteristic that they build in new types of sensor information. So, just suppose when I strain something, it becomes fluorescent, and I can look at the degree of strain by the fluorescence. Or I know I can build these systems using exactly the same technology to have lasers built in, to have waveguides built in, to have wires built in, hence have magnetic fields built in, microfluidic systems built in. And one of the nice things about the soft systems is that, for example, we can build a tentacle, and the tentacle can go out and sort of sniff this pile of white powder, and then can sample it, and then can drip sulfuric acid on it if that's the right thing to do. That's not trivial to do when you're dealing with a system that's hard because you don't know what you're going to be dealing with. So I think the whole notion of building multifunctional materials that are nonetheless elastomeric and will stand up to this is actually pretty short term and very interesting and will dramatically expand the field.
So perhaps one more question.
Yeah, George, just out of curiosity, if we think of our brains, where would you put our brains in your category? It's a soft material, soft matter, but it has very complicated functions, and it learns and it does things by itself. So how would you say about the brain?
I have a sort of theory that I sort of believe, which is the following. That if I think about, I'm a chemist, so I start thinking about molecules. And if I think about a cell is a collection of chemicals. And the chemicals are reacting. The chemicals themselves, the molecules, are not alive. The reactions are not alive, but the collection of molecules and reactions is alive. We don't really know what that means, but it's to me very interesting. It may just be something that happens. An analogy is that life is just like a flame. You have a complex set of reactions, stable so long as you feed it oxygen, methane, or glucose, and peanut butter, and it creates life, and that's what life is, and then maybe that's all that's what life is. If that's true, which I actually think it is, then what is a brain? A brain is a collection of cells. And the cells are just collections of reactions that are happening. So us, sentience, self-awareness, love, hate, all of that may just be a spontaneous activity of complex systems that happens to have had a extended persistence in the environment in which we live. It's a thought that makes me as uneasy as it probably makes others of you. But, is there a difference between, a flickering flame of wax gas in the swamp in Siberia and Beethoven thinking about the ninth? Well, I don't know. So that's something for those of you who are young. Yeah, think about it.
So on that note, it's good to have a homework assignment of sorts. One more thing before we conclude. There's going to be a reception right outside, so as you come down the stairs and you exit, please join us for the reception. We also have a memento, Arizona State University, Ira Fulton Schools of Engineering, in appreciation of George M. Whitesides, Dean's Lecture Series, April 4th, 2018. Let's thank Dr. Whitesides one more time.
Thank you. It was kind of you not to say memento mori.